Section 8.1, Exploring Exponential Models. Our objectives are to model exponential growth and decay. So let's talk about exponential functions first. A function with the general form of y equals ab to the x power, where x is a real number, and a, this value here, we're going to call the initial value, and b is going to be called the growth or decay factor. Now, in order for something to be an exponential equation, we have to have an exponent variable as an exponent. So this right here is an exponent, remember? If we don't have a variable as an exponent, then it's not an exponential function. So keep that in mind. If the equation is an exponential growth equation, then that b value, your growth factor is what we would call it, would have to be greater than 1. If the equation is a decay equation, then your b value would be in between 0 and 1, so a fraction between 0 and 1, or a decimal. So that would be growth, and the other one would be decay. So let's look at the first one. We have y equals 2 to the x power. Notice that my a value in this case would be equal to 1 because there's nothing in front of the 2. My b value is equal to 2. So since it's equal to 2 and greater than 1, we know this is going to be exponential growth. Now, if I want to graph this, we can plug in values for x and see what our y is. So let's start off with 0 from our table. 2 to the 0 power. Remember that anything to the 0 power is really equal to a value of 1. So this is really 2 to the 0 power, so that equals 1. If I do 2 to the first power, that's equal to 2. 2 squared is equal to 4. 2 to the third power would be equal to 8, and so on. So if we do the negative side, then if I had 2 to the negative 1, remember when we have a negative exponent, that means that we are going to put this in the denominator. So this is really 1 over 2 to the first power, so 1/2. So this would be 1/2, or you could write 0.5. The next one, 2 to the negative 2 power, would be equal to 2 to the negative 2 is the same thing as 1 over 2 squared, which is really equal to 1 over 4. So this would be 1/4. And the next one would be 2 to the negative 3, so that's 2 to the third power is 8, so we really have to do 1 over 8 and keep going. So if you think about this problem, notice that when I plug in positive numbers, my graph y values are going up very rapidly. And also notice when I plug in 0, I get 1. And also when I plug in negative numbers, I don't get a negative answer, I get fractions. So if you think to yourself for a minute, can I ever get a value of 0? The answer to that question would be no. So if I go to my graphing calculator and plug this in, I have y equals 2 to the x power for my graph. So if I look at my table, so these were the table values that I got right here. So notice we have 0.5, 0.25, and so on. So if I keep scrolling down for these values, I know that if I look at my graph, this is what it would look like. So the y values are shooting up. And what are these values as we go on the negative side for x doing? If I hit trace, notice that my values are getting closer and closer to the value of 0, because remember, this just really means we're moving the decimal place 5 places to the left. But the question is, can I ever get 0 on my graph? And the answer is going to be no. So when that happens, we actually call that an asymptote, which I'm going to write down here. So an asymptote is a line, and we usually make it dotted. So it's a line the graph approaches, but doesn't touch or cross over. So if we go back up, let's go ahead and graph this. So for my graph, we first need our x and our y axes. So I'd make this my x-axis, and this will be my y-axis here. So for this, my values of y as I get in the go in the positive direction are going up very rapidly. So I'm going to go by just ones on my graph right now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'll make this 10. So this would be 15. Okay, so if we graph this, we have the point 0, 1, and then we had the points 1, 2, and then 2, 4, and then 3, 8, and then if we did 4, we would have 16, so that's going to be off our graph. And then backwards, -1, we had equal to a half, and these values are getting smaller and smaller and smaller, but they're never going to be able to cross over that x-axis right there. So my graph would look like this. And right here on the x-axis, we have an asymptote. And notice that we call this a horizontal asymptote because it's a horizontal line. So I know that my graph is going to be coming close to this line, but it's not going to touch or cross over. So this is a horizontal asymptote. And in this case, it's y is equal to 0. Let's also talk about the domain and the range. So your domain remembers all possible values of x that you have. Well, if you look here, we could plug in positive numbers, we could plug in 0 and negative numbers. So my domain for this is all real numbers. Remember, we use this symbol right here. And then my range, remember the range stands for all possible y values. Now if you look here, our range values are values that are above 0, but we can't be equal to 0 because we have the asymptote there. So our range is going to be y is greater than 0. So that would be exponential growth. So let's look at the next problem that we have right here. We want to graph 10 times 0.5 to the x power. So for this problem, my a value is equal to 10. My b value is equal to 0.5. Since my b value is less than 1, but in between 0 and 1, I should say, I know this is going to be exponential decay because my decay factor is a half. So for this, if I want to graph this, I can use my graphing calculator in my table to help me. So we're just plugging these values in. So if I have 10 times 0.5 to the 0 power, that's going to be equal to, so 0.5 to the 0 is 1, and 1 times 10 would be 10 because we have a value in front. If I plug in 1, then I would have 10 times 0.5 to the first power, so 0.5 to the first power is 0.5 or a half, so 10 times a half would give me a value of 5 because you're dividing 10 by 2. And if we did the same thing, we could keep going. So if I plug in 2, I would get 2.5. This is going to be 1.25. And then this value up here is going to be 20. We have 40 and then 80. So notice that as I plug in values of x that are positive, my graph is getting smaller and smaller. And as I plug in values of x that are negative, my graph is getting larger. So it's the opposite of what we just did on the last graph that we have. So let's go ahead and look at this. So I'm going to change the scale in my graph to go by tens or by fives because it's so large. So I'm going to make this 10. This would be 20, 30, 40, 50, 60, 70, and that means I missed 80, which would be up here. So for this graph that I have, I know that I'm starting off with the value of 0, 10, which would be right here. And then I have negative 1, 20, negative 2, 40, and then negative 3, 80. And then 1 has a value of 5. And then these values are going to get smaller and smaller. So now my graph goes something like this. Whoops, I was a little bit off there. So this should have been here, and then this would be here. Sorry about that, I didn't realize I was a little bit off. So now my graph is going this way. So notice as we go from left to right on our graph, our y values are decreasing, whereas in the first one, as we moved from left to right on our graph, our y values were increasing. So that's how I knew it was exponential growth. And because these are decreasing as I move from left to right on my graph, that's how I know it's exponential decay. And again, even if I were to graph this in my calculator, y equals, so I have y equals 10 times 0.5 to the x. And if I go to my graph, I'm going to hit zoom 6. So here's what my graph looks like. So notice it's coming down, and it's not a very good window because remember at 0 we had a y value of 10. So if I change my window y values, I'm going to go up to 80 and then hit graph. Oops. I accidentally put 8. I meant to put 80. So now if I hit graph, notice we have a larger graph to look at. So my y values are coming closer and closer to this value of 0. However, I'm never going to be able to reach 0. So that means we have a horizontal asymptote at y equals 0. So I usually abbreviate horizontal asymptote as HA. So our horizontal asymptote is, again, y equals 0. My domain is still all real numbers because I can plug anything in for x, and my range values are still values of y that are greater than 0. Okay, so those are the two types of equations that we're going to be looking at. So if you know the rate of increase or decrease, which is your r value, you can find the growth or decay factor by using the equation. If it's growth, it would be your b value is equal to 1 plus your rate. If it's decay, it would be 1 minus your rate because your rate would be negative. So for these next examples, it says find the annual rate of change, find the corresponding growth or decay factor. So if we look at number 1, for this problem, I'm given positive 25%. So since that means we're going to be increasing by 25%. Because of that, I know this is going to be growth without even doing anything. So if I solve this, I'm going to solve the equation to find my growth factor, which is your b value, is going to be 1 plus your rate. So in this case, b is equal to 1 plus 0.25. So that means that my b value is equal to 1.25. So this is my growth factor. So then for the next one, I know that this is a negative percentage. That means my rate is equal to negative 0.15, because remember we had to write as a decimal. This was a rate equal to 0.25. So for this one, since my rate is negative, I know it's going to be a decay factor. So b is equal to 1 plus your rate. So b is equal to 1 plus negative 0.15. When I solve this, I get b is equal to 0.85. So that means this is my decay factor. If I look at number 3, for this problem, I have plus 300%. That means my r value is going to be equal to, move your decimal place 2 places to the left, so 3. So for this, if my R value is 3, I know this is going to be a growth because we're growing by 300% is what that means. So b is equal to 1 plus 3, so b is equal to 4, so this is my growth factor. And of course, if we're given our growth factor, we can do the opposite to figure out what our rate of increase or decrease would be. So let's look at some examples. The population of the United States in 2000 was about 281 million with an average annual rate of increase of 1.24%. So this tells me my rate. We want to find the growth factor for that year. So in this case, if we want to find the growth factor, we know that our rate is equal to, a positive 1.24%. So the first thing we want to do is write that as a decimal. So for my decimal, we would end up with moving my decimal 2 places to the left. So 0.0124 is actually my growth factor. Or sorry, and that's not my growth factor, that's the decimal. So if I want to find my growth factor, I have to do b is equal to 1 plus my rate, 0.0124. So that means my growth factor is 1.0124. So that's the factor by which I'm growing. The rate at which I'm growing is different, which is 1.24%. So be careful of how you say that. So then remember that the next part says suppose the rate of growth continues to be 1.24%, write an exponential function to model the US population. So remember, we're using the equation y equals ab to the x. A stands for our initial population. So we're starting off with the fact that we know in 2000 it was about 281 million. So instead of writing 281 million, I'm just going to use 281, remember, to make my answers in millions. So I have y equals my initial amount, which is 281 in 2000, times my b, which is what we found in the last part, my growth factor, so 1.0124, to the x. So this right here would be my equation. So if we want to estimate the population in 2015, well, I need to figure out what the x value is that corresponds to that. So 2015 minus 2000, because that's what we start off in our equation, is equal to an x value of 15. So that means I'm plugging 15 into my equation. For x, that is. And then all I have to do is evaluate this using my calculator. So I have 281 times 1.024 to the 15th power. And be careful that you make sure to put parentheses in the correct places, otherwise you might end up with something that's not correct. So enter. And we end up with about, oops, I think I missed a one in there. Here we go. So we end up with 338 million people. So that's what I'm going to write. So in 2015, that's my estimated population. Let's do the next one. It says we want to write an exponential function in the form of y equals ab to the x for the graph that includes the points 2, 2, and 3, 4. So now for this, the easiest way to write an exponential function would be to use our graphing calculator. So if you remember in our graphing calculator, if you go to stat and hit enter and edit, we have these lists that we can enter. So I'm going to highlight it, hit clear, and push down to clear it. And I'm going to enter my points that I have. So remember, your list 1 are your x values. So I have a 2 and a 3. And in list 2, I have the y values, which are 2 and 4. So if I go to stat and arrow over to calculate, notice that we have linear regression, quadratic regression, cubic regression, quartic regression, and then if we keep on going, all the way to right here, notice it says EXP-REG, which means exponential regression. So if I hit enter and enter, this comes up with my equation. Notice it's y equals a times b to the x power. So your a value is 1/2 and your b value is 2 in this equation. So let's go ahead and write that in. So we were using EXPREG in our calculator. So the equation would be y equals 1/2 times 2 to the x power. So I know that if I look at my b value is equal to 2. So I know that this graph is going to be exponential growth. So number 3, we're doing the same thing. It says write an exponential function of the form y equals ab to the x for the given table that we have. So you would do the same thing. You would plug these into list 1 and plug these values into list 2. So I want you guys to do this on your own. So let's look at the next example. It says the NCAA holds an annual basketball tournament. The top 64 teams in Division I are invited to play each spring. When a team loses, it's out of the tournament. So how many teams are left in the tournament after the first round of games? So let's think about this. So the first round, which is round 0, we have 64 teams. So after the first round, then, well, half of the people are gone because remember that you have one person moving on, so that means that 32 would be left. After round 2, then 16 teams are left. And after round 3, 8 teams are left. And round 4, 4 teams would be left. That's the final 4. And then after round 5, you have 2 teams left for the actual championship game. So then after that next round 6, you would have 1 team left. So after the first round, there are 32 teams remaining. And then it says how many teams are left at the second round, which we just found. So then 16 teams would be remaining. And then how many rounds are played in the tournament altogether? So altogether, notice that there were 6 rounds that we played. And this is actually an exponential decay graph. Each of these values are discrete, but let's say that, you know, if we wanted to make an equation for this, if it didn't have to deal with basketball, if it was something else, then you know that each time you're decaying by a factor of 1/2. So that means this would be my decay factor, because you have half the teams left. So you know that your graph would be coming down looking something like this. So that means that your rate at which you are decaying is 50%, since your growth or decay factor is 1/2. So the rate would be equal to negative 50%. So let's analyze some of these functions. Without graphing, we want to determine whether the following functions represents exponential growth or decay, and then we want to find the growth or decay factor. What is the rate at which the graph grows or decays? So if you look at number 1, so I want to find my b value. My b value is 5. Since it's bigger than 1, we know this is a growth factor. Now I want to figure out what the rate at which we are growing is going to be by. So we use the formula b equals 1 plus your rate. So in this case, since b is 5, we have 5 is equal to 1 plus r. So if I solve, I would get, subtract the 1, so 4 is equal to r. So that means that that's going to give me my rate, but this is we had to multiply this by 100 in order to get the percentage. So that means the rate at which you are growing by would be a positive 400%. So if you look at number 2, I see my b value is 0.95. So since it's a decimal in between 0 and 1, this is a decay factor. So then for this, to find my rate at which I am decaying, I have to plug this in to solve. So I have b equals 1 plus my rate, so 0.95 is equal to 1 plus r. So this time I'm subtracting the 1. So when I do that, I get minus 0.05 is equal to r. So if I write this as a percentage, that means that we are decreasing by 5%. So multiply that by 100 or move your decimal place 2 places to the right to get that percentage. So then for number 3, 5/4, if you don't know, write it as a decimal. This is a b value equal to 1.25. Because it's above 1, we know this is a growth factor. So just because you have a fraction doesn't mean it's exponential decay. So in order to find the rate at which we are growing, we use the same formula. 1.25 is equal to 1 plus my rate. So in this case, when you subtract the 1, you end up with your rate being equal to 0.25. So that means that the rate at which I am growing is going to be positive 25%. And so then the last one, we have a b value of 1/2, which you know is exponential decay. So it's decay factor. So to figure out the rate at which we are decaying, we do, remember, b is equal to 1 plus your rate, so 1/2, or if you want to write 0.5, that's fine. Subtract the 1, and notice you get negative 0.50, if you want to write, equals your r. So that means the rate at which we're decaying is negative 50%, which makes sense because if our decay factor is 1/2, that means our rate should be decreasing by 50%. So depreciation is a word that means the decline in something's value from age and wear. When an item loses about the same percent of its value each year, you can use an exponential function to model its depreciation. So since we're doing exponential models, still we're using y equals ab to the x power. Now these are different than the other ones that we did were exponential growth. So the initial value of a car, it says, is $20,000. After 1 year, the value of the car is $17,000. Predict the car's value in 6 years. So for this one, it says the initial value of the car is $20,000. So I know that the initial value means that's my a value, so $20,000. And then it says after 1 year, the value of the car is worth $17,000. So we have $20,000 for A, so that means that at year 0, I have $20,000. And after 1 year, we're at $17,000. So for this, I know that it's going to be y equals 20,000 times something to the x power. I want to figure out what that something is. The easiest way that I would do this is you can just plug it into your calculator like we did for the other one and just do your stat plot. So if I go to stat, enter, and over here, so I would put it in my stat plot, and then you can do stat, calculate, exponential regression. Oops, I believe it's 0. So exponential regression, enter, and notice I get, oops, I put too many zeros in there, I didn't realize. And this is the equation that we end up with. So I'm going to put 0.85 here. So if I want to predict the value of the car in 6 years, that means I want to figure out when x is equal to 6, what's the y value equal to? So again, you can just plug this into your calculator and solve, and you should end up with the value being equal to $7,543. So the next example says the deer population increases at a rate of 3% per year. There are 300 deers in your area. Write a function that models the deer population in your area. How many deer will there be after 10 years? So now the key words right here are the fact that it says it increases at a rate of 3% per year. So it didn't give me the the growth factor, but it gave me the rate at which we are growing, and I know it's growing because it says the word increase. If it said decrease, then I know it'd be decay factor. So the rate at which I'm growing is at 3%. So if I write that as a decimal, that would be 0.03. So then remember, we're using the equation y equals ab to the x. So I don't need the rate, I need my growth factor. So to find my growth factor, b equals 1 plus your rate. So b is equal to 1 plus 0.03. So b is equal to 1.03. So that's what I'm going to use in my equation. It also tells me that there are 300 deers in the area. So that's what I'm going to start off with, my initial value. So my equation is going to be y equals 300 times 1.03 to the x. So that's the equation. And then we want to figure out after 10 years, how many deer are there? So that means when x equals 10, plug this into your calculator, and you would end up with a value of y being equal to 403 deers. Make sure you practice plugging that into your calculator, because a lot of times students get these examples wrong because they can't plug it into the calculator correctly. And one last example. It says a new iPhone that sells for $600 depreciates by 20% each year. We want to write a function that models the value of the phone. What is the value of the phone after 10 years? So we're depreciating by 20% each year, which means that that's my decay percentage rate. So the rate at which I'm decreasing, and I have to remember to put negative, is going to be 20%. So that means R is equal to negative 0.20. So if I want to figure out the b value, so my decay factor, b is equal to 1 plus r, so b is equal to 1 plus negative 0.20. That means my b value is equal to 0.80, which makes sense because we know we're depreciating, so it's a decay factor. So y equals ab to the x. I know that I'm starting off with, it says that iPhone sells for $600, so a is my equal to 600, which is my initial amount. So y equals 600 times my b, which is 0.80 to the x. So this is the equation, and if I want to figure out in 10 years how much I'm going to be worth, I'm going to be doing y equals 600 times 0.80 to year 10. So in 10 years, your iPhone would be worth $64.42. So of course, this isn't a real problem. I don't know how much your iPhone would be really worth in 10 years, but it's just a problem that I made up. So make sure you bring this with you to class, and we're going to go ahead and continue to do more examples in class.